Hey, everybody. Um, Happy Tuesday, I suppose you're probably watching this video for the first time. Um, I'm going to go through the answers that I got for the practice AP Calculus test, which, by the way, if you are watching this on Tuesday, is 1 week from today, the real deal. But the AEB version of a practice that was come up with by someone, probably a calculus teacher would be my guess. And there's a couple points that I'm going to point out as I go through this that I don't think would probably be asked, at least not in this way, on the AP Calculus test. But there's a lot of good stuff that is here. Um, I thought this one was a pretty high degree of difficulty given the amount of time that you would have for some of these, especially for the second one. Question 2 felt more like a 25-minute question than a 15-minute question, but I will talk about that when we get to it. Part A of number 1, and by the way, I just have my answers here, so you probably either want to have a PDF of the questions open in a tab or have the questions printed off to follow along. But part A is asking for the derivative at time equals 8, and we're given a table of values. We are not given a function, so taking a derivative isn't an option, but we can use the table of values. The two times that are closest to 8, I went with 9 and 7. So just a simple slope y2 minus y1 over x2 minus x1 to get 2 butterflies per day. And it does say use correct units and interpret the meaning. So if all you write down is 2, you're not going to get very much for that. But to say butterflies per day, and then this is the rate the population is increasing, or this says that 2 more butterflies showed up on the 8th day, or something like that. Part B, explain why there must be at least one time on this interval between 0 and 14 such that the derivative is equal to 1.5. This is a mean value theorem problem. And notice that I didn't cite the mean value theorem, but I used the mean value theorem that says there's a time when the instantaneous rate of change is equal to the average rate of change. Now, when I did this problem, I foolishly hunted for a time interval over which the rate of growth of the population was 1.5 times as big as the rate of time. And I found one between time equals 3 and time equals 9, where the population grew by 9 over 6 days, which is a growth rate of 1.5. And so I said that on this interval between 3 and 9, there must be a point where the instantaneous rate of change is 1.5. But then I looked at the answer key and saw that if I had just done that between 0 and 14, that worked. And that was a lot easier to find because they told me that they wanted to go between 0 and 14. So my answer is okay because the interval between 3 and 9 is on the interval between 0 and 14, but would have been easier to go with the endpoints. Part C, I think is a goofy question because I don't know what the integration of a population would tell us. I get an answer of 76, but I don't know what that is. 76 doesn't make any sense to me. So I don't think they would ask something like this, at least not in this context. If the table was given a rate, if the table was a velocity set of data or something like that, then integrating a rate gives us a quantity. So I don't know what this represents, but we can do it. I've got rectangles. They gave me the intervals between 0 and 5, 5 and 9, and 9 and 14. So the first number I have here is how wide those intervals are. And then the second number is the height of those rectangles, the value of the function at the left side or at the lower side. And then this is an underestimate because our function is increasing, and a left Riemann sum with an increasing function will yield an underestimate. Part D scared me at first because we're looking at the rate that it's increasing is decreasing, which means we're talking about second derivatives. And the second derivative of that function at first I thought was going to be bad, but it's actually not all that bad. Just a little bit of chain rule to deal with on this one. And so I went ahead, I took the derivatives, plugged in 8, and hoped that I would be able to tell if they were positive or negative. For the first one, it was just e to the 1 minus 0, and so that's just e, which is bigger than 0. And the second one was 1/7 of e minus 4. And as we've talked about in class, as long as you know that E is 2 point something, you're okay. 2 point something divided by 7 is less than 4. And so when I subtract 4, I get a negative value. And since the second derivative is negative, the first derivative is positive, it is increasing, but at a decreasing rate. Part E, let's see. When I did this one the first time, I started by taking the derivative, and I got something that looked like this. There's chain rule happening here. I'm taking the derivative with respect to time. We're talking about time here. This is, I guess it's related rates. It's not very obviously related rates, but it is. We know how fast the temperature is changing. We're trying to find how fast the population is changing. And at first I wasn't sure how to deal with this because I don't have the temperature. I don't have this mysterious K value. And so I went back and I looked at the problem again, and I realized that when the temperature is, or sorry, when the number of bees is 100, so when this function is equal to 100, the function that we're given, it just looks like this, which means at that time when the population is 100, this radical that shows up in my derivative has a value of 2. And so if I'm trying to find what is the value, how fast is the population changing at that moment, well, at that moment, after I've taken the derivative, I can plug in 2 for this, and then we're given that the rate of change of the temperature is also 2. And so we've got 50 divided by 2 times 2 to get 50 bees per day as my rate of growth. I thought that one was a little bit nasty, but not completely unreasonable. And then question 2, a pretty standard AP calculus kind of a question on the AP test. They like to put graphs that have segments and parts of circles and stuff like that. And so as we do this problem, I'm given that g of x is 3x plus the integral of f between 2 and x. And so I just plug in 8. The work that you see here is just part of a circle plus a rectangle plus a triangle minus a triangle. The triangle between 5.5 and 8 is below the axis, so I subtracted that area and came up with this as an answer, 22.5 plus pi over 4. And then after doing this one, I realized that there's a lot of symmetry to this graph that I didn't notice initially. Between x equals 5 and x equals 6, there's equal sized triangles above and below the axis. And the same thing between x equals 7 and x equals 9. There are equal sized triangles lying below the axis versus above the axis. And so I started to cancel some stuff out maybe a little more wisely as I moved forward. But then the second part of part A, g prime of 8, it's almost straightforward fundamental theorem of calculus. It's just a little bit disguised because it's not just g is the integral of f, but rather g is 3x plus the integral of f. And so the derivative, we've got this extra plus 3 that we usually don't have. But the derivative of the integral still is f of x. And actually, this expression is going to be useful, I think, twice more before we're done with this one. But anyway, to finish off the rest of this one, to find g prime of 8, it's just 3 plus f of 8, and we look at the graph and see that that is 0. Part B, this is the one that ended up being really time consuming, at least the way that I did this. There may have been a more efficient way of doing this, but I couldn't think of it. Critical numbers, if I want to find where a function has a maximum value, and by the way, that 3x in the equation really messes things up for us because I can't just look at the graph of f and say, well, this is the derivative, so this is where it's increasing and that's where it's decreasing. At least I wasn't able to figure out how to do it other than doing what I'm doing, and that is I have critical values when the derivative of g is either equal to 0 or doesn't exist. Well, its derivative is 3 plus f, and so it exists everywhere, so that's not a problem, but then it's equal to 0 when f is equal to negative 3. So look at the graph and see where that happens. That's at negative 1 and 7. And then if I want to say that this is the maximum, I've got to consider the endpoints as well. And so I've got, these are my two critical numbers, but then I also have to take a look at the endpoints. And this was really time consuming for me to go through and look at, just plugging in the values, not a big deal. But then this integral, we're looking at parts of circles and parts of, well, I guess that was just parts of circles, but then for the rest of them, it's triangles and rectangles and maybe even trapezoids. And so this was painstaking for me to do. But then once I was done with it, thankfully, there were lots of negative values and smaller values. This one was the biggest one, which means that's where the maximum occurs. For part C, we're looking at what the limit of the derivative of f is. So we're looking at the graph of f and asked questions about the limit of the derivative at a spot where you've got a part of a semicircle switching into another semicircle, and what's happening at that spot where those semicircles meet. From the left, the slope is approaching vertical. From the right, the slope is approaching vertical. At that point, it's a vertical tangent line. And I don't think they would ask something like this on the AP Calc test because they tend not to get into the issue of the limit equals infinity versus the limit does not exist. But technically, the limit does not exist. And my justification is that neither of the sided limits exist. From the left and from the right, it's going to infinity, which doesn't exist. Therefore, the limit does not exist. And I realize that's a little shaky because we want to say that it's infinity, but technically that doesn't exist. And then finally, part D, I was really hoping this would be L'Hopital, and it was, but I had to check and make sure first. I had to find what the limit of the numerator and the denominator were separately. They were both equal to 0, which means L'Hopital does apply, which is good. But to me, having you do this again seemed a little superfluous because we already did it on part A. And so here we are again, actually on A and B. We were doing a lot of areas on this problem, which I wasn't a big fan of. But once you do them, it turns out to be equal to 0. We apply L'Hopital. After applying L'Hopital, all of these constants just go away when we take the derivative. So that cleaned up kind of nicely. Denominator was equal to 1, so we're just dealing with the numerator. And then here again, that G prime is 3 plus f. And so I'm just plugging 6 into f, looking at the graph to find that it's equal to -1. And then the calculation leads to 32. Those are my answers. I'm also going to post the answers from the person who I assume wrote this question. So you can take a look at those. They're definitely a little bit different than mine. I think we got all the same numerical answers, but some of our justifications were different. And then also, I'm going to say it now. And by the way, this is Thursday afternoon that I'm recording this, so a lot of time for me to forget about this, but I'm going to try to remember to let you guys know. I posted a gigantic document from AP Central that has a whole bunch of information about AP tests this year, not just calculus, but all AP tests, and how to make sure that you're registered and the day of and practice and just making sure the technology works and all kinds of stuff that they're dealing with. I was going to try to summarize it, but my summary was ending up about as big as the document was in the first place. So I posted that. Take a look at that, especially if you're concerned or worried about the AP test coming up in a week. Otherwise, I think I'm going to sign off for this. Moving forward, we'll take a look at some solids of revolution and some other topics, but I will just warn you, they're probably going to be in the context of AP questions, so we can get more bang for our buck. We can get practice and we can look at some old skills at the same time. So that is all I'm going to do today. Hopefully you're having a great start to your week, and we'll talk to you later. Bye-bye.